All right, this next video is on the Atwood machine, which is basically just two objects connected over a pulley. It's kind of how elevators work in like a very basic sense. So usually we have some sort of pulley, and we say that it is massless and frictionless. And we start with our simplest model. Later on in the year, we'll actually talk about what happens if the pulley is not massless. And then there's usually two objects hanging, and I'm purposefully drawing them separate sizes so that we can kind of say that M1 is going to be larger than M2. Okay. Now, just like most of our objects, we can either draw each object its own free body diagram, or we can do this system as a whole. And I think by now we've figured out that usually it's that tension force that then becomes internal to the system. So M1, we're going to have a force of gravity and a tension force. And I'm purposefully drawing that tension force smaller because since M1 is the larger force, I hope it makes sense. It does to me that this is going to accelerate downwards. So I need a net force downwards. Now, everything is connected, so if M1 is accelerating downwards, that means M2 is accelerating upwards. Okay, so I still have a tension force, but then I have like an even smaller force of gravity. And through Newton's third law, this tension force and this tension force are the same. Now, very similar to the half Atwood, what gets confusing is that we have an acceleration down, but also an acceleration up. So even though our forces are all in the y direction, we're accelerating in different directions. So this is another situation where doing that rotation of the free body diagrams can be really helpful. So what I usually do is I usually make it so that each free body diagram I am rotating sort of 90 degrees, right? And I want to rotate these so that my tension forces are pointing in towards each other since they're connected by that string. So we have Ft and then Fg2. Now, what this shows me is that even though Fg1 and Fg2 are pointing in the same directions, as far as the system as a whole, they're pointing in opposite directions. So since Fg1 is in the same direction as that initial acceleration, I'm going to say for my whole system, the acceleration is to the left. Okay? And this is where it's really important to keep direction of acceleration, or positive versus negative, super consistent. Okay? Because even though the tension force is up for M1, I'm going to call it a negative here based on my direction of acceleration. So my net force equation for M1, luckily I only need one since we only have one direction, is going to be Fg1 minus Ft is M1A. And then for the second mass, M2A, I'm going to have a tension force minus Fg2, again, because I'm making sure that I'm being consistent, right? Keeping direction of motion consistent. And of course, these tensions are equal, and these accelerations are equal. Now, I could definitely solve from here for acceleration if I needed to, but I would have to do some sort of substitution. And I could definitely do that. It's not anything wrong with that, but it's not the fastest way, and sometimes time is not on our side. So if we can do things quicker, that's awesome. Okay. So that's where the M1 plus M2 system comes in, because that tension force is now internal. So these two tension forces kind of disappear. They're internal, and we make it so that we have one big system. And on that one big system, we have a force of gravity pointing one way and a force of gravity pointing the other way. So again, showing us that even though those gravitational forces are both pointing down, they are fighting each other as far as the acceleration and net force of the system are concerned. So my net force equation here, of course, has to include both masses of my system. And I'm going to say direction of acceleration is positive. Probably should have labeled that positive there. Okay. So I'm going to have an Fg1 minus an FG2. Got to add my masses together because they are both in my system. So M1G minus M2G all over M1 plus M2 is A. So here I just had to do some simple rearranging to get acceleration, whereas down here I'd need to do some substitution. Okay, now once I have that acceleration, I can totally substitute into either of these equations to find the tension. So let's go ahead and do that. It's going to look messy, but it's okay. It's not going to simplify very nicely. Since tension's positive here, I'm going to use this equation to solve for tension. Doesn't matter which one we do. So tension has got to equal M2A plus M2G. Now A would likely not be a given variable, so I'm going to substitute in that whole big ugly fraction. And I have M1G minus M2G over M1 plus M2 plus M2G. And like I said, it's not pretty. There might be ways to simplify it further, but we wouldn't really need to. So that's going to be it. Really, these problems don't get much more complicated than that. Sometimes we talk about adding masses, whatever. We are always going to accelerate in the direction of the larger object. And remember, that acceleration isn't going to be impacted by the direction of motion. So even if I gave M2 an initial push downward, it wouldn't change anything about what I just did. It would just mean that initially I'm slowing down, and then this whole system reverses direction and speeds up. So not too bad. Just the tricky part is that kind of direction thing I talked about in the beginning. So that is Atwood Machines.